Welcome to another session of Digital Signal Processing lecture series, and this is Ram Prasad Pujari. In this session we'll talk about two important elementary signals known as impulse function and the second one unit step function. So this is the agenda for today's presentation. We will initially look at two important elementary signals in the discrete version form. The first one is unit impulse, or it's also called as unit sample sequence or a delta function, which is denoted as delta of n. And similarly, the second elementary signal that we are going to discuss is unit step sequence, which is denoted as u of n. These are elementary signals. They have a standard notation, unlike arbitrary signals which are denoted by other notations like x of n, etc. We will also look at how delta of n and u of n are related to each other, or how you can get delta of n from u of n, etc. We will also look at the significance of these two, what are the uses where it's applicable. First we'll look at unit impulse or unit sample sequence. This is an important signal in signal processing. Maybe even if you're talking about the continuous time version or analog systems or discrete time systems. So in both the places you come across unit sample function. In the case of analog version, you represent unit sample or unit impulse function. We don't call it as unit sample, the unit impulse function, which is denoted as delta of t, whereas here we represent it as delta of n. And this is the representation, this is the function delta of n equal to 0 for n not equal to 0, and delta of n equal to 1 for n equal to 0. Now in this case, this has got only one sample at n equal to 0. But when you compare it with the continuous time version, in a continuous time version we have a pulse at t equal to 0. But so that pulse, the area under the pulse will be equal to 1. Whereas here it's the amplitude, because we are talking about discrete time version. So this is delta of n. At n equal to 0, the amplitude will be 1. So you can also perform time shifting operation on this, which we have seen in the last session. You can shift it to the left by one sample, you get delta of n plus 1 as shown here. And similarly, if you shift delta of n to the right by one sample, you get delta of n minus 1. So these are shifted version of delta of n or unit impulse or unit sample sequence. Now any arbitrary sequence, for example if you take x of n, and this x of n can be represented in terms of impulse function. So this is where the convolution formula begins. So if you look at the convolution formula that we discussed in the first session of DSP lecture series, so there the starting point of this derivation is representing arbitrary signal in terms of impulses. So as you can see here, I have taken a signal x of n which has 3 samples at n equal to minus 1 with an amplitude 2, at n equal to 0 with an amplitude 3, and at n equal to plus 1 with an amplitude 4. Now I can represent this by 3 different impulses. The sample at x of 0, so that I can represent with the help of delta of n with the scaling factor 3. The 3 is nothing but the amplitude of this particular sample. And similarly, this particular sample, the sample at n equal to minus 1, I can represent using a left shifted version of delta of n, that is delta of n plus 1. But the scaled version, the scaling factor is 2, which is nothing but amplitude of this sample. And similarly, the sample at n equal to 1 of x of n, that is x of 1, can be represented by using delta of n minus 1 with the scaling factor 4 into delta of n minus 1. So that means I can represent x of n, the 3 samples, 3 non-zero samples, with the help of 3 different impulses. And if you look at this is basically a sum of scaled time shifted impulses. This is how we say, so this is a sum of scaled, because there is a scaling factor here, amplitude scaling is there, and the scaling factor, it's nothing but amplitude of the corresponding the samples of x of n. So 2 into delta of n plus 1 plus 3 into delta of n plus 4 into delta of n minus 1. So that means any arbitrary signal x of n can be represented in terms of impulses as shown here. So this is the beginning to a convolution formula that we saw in the first session. This delta of n also exhibits some of the properties, and 2 of them I have shown here. In the first case, an arbitrary signal x of n is multiplied with an impulse, and you can see that in this case summation x of n delta of n, that's equal to x of 0. As you know that delta of n will be 0, that is when n equal to 0, and so when n equal to 0 this function is 1, so therefore you end up getting x of 0. And similarly, there is another property called as a shifting property, where delta of n is shifted by k samples. Now again, this delta of n minus k will be equal to 1 only when n equal to k. So when n equal to k, so this becomes x of k. So you end up getting x of k here. So to measure k, the sample of x of k, so then we can use a shifting property here. So that's about delta of n, and similarly this is another important elementary sequence called as unit step sequence. So unit step sequence has a very important role in control systems. To understand the behavior of the dynamic system, unit step input is given. Before that, we'll look at the unit step sequence function in the discrete form. Unit step sequence is represented as u of n, and that's equal to 0 for n less than 0. That means for negative time instants it's a 0, and starting at n equal to 0 up to infinity, the amplitude will be equal to 1. So this is how we represent unit step function, and it's illustrated here. So this is the sketch of unit step sequence. This is also a causal sequence, a right-sided sequence, and this is also an infinite duration sequence. This has got infinite number of samples starting at n equal to 0 till infinity with an amplitude 1, and you can see that there is a jump here. This unit step sequence is also called as heaviside step sequence, and so these are u of n plus 2, u of n minus 3 are the shifted version. This is left shifted by 2 samples. The sample starts at n equal to minus 2, and similarly u of n minus 3 is the right shifted sequence, where samples start at n equal to 3 goes up to infinity. Now I can get a finite version from these two. I can subtract u of n minus 3 from u of n plus 2 as shown here. I end up getting a finite duration sequence as shown here. So you end up getting only 5 samples starting at n equal to minus 2 up to n equal to 2, and sample at n equal to plus 3 gets cancelled here because of subtraction. So that's about unit step function. And now, just to understand the uses of impulse and step function, the first very important use of impulse function is in convolution. As you saw that in the convolution formula, we have something called as an impulse response. So that means the convolution formula is used to obtain the response of an LTI system whose impulse response is given. And what is impulse response? Impulse response is a response to an impulse function. So that means once impulse function is applied as an input, the response that you get is denoted as impulse response. It is said to be impulse response. Now, why it is important is, once we know the impulse response of a system, then we can find the response for that system for any arbitrary signal x of n. So that's the advantage of this impulse response. The second use of impulse function is in sampling. As you can see in this particular expression, the sampled signal can be obtained from analog signal by multiplying it with a train of impulses as shown here. So this is the train of impulses. This is the sum of shifted impulses, and that will give you a train of impulses, and that is multiplied with analog signal x of t to get a sampled signal. So this is another use of impulse function. When it comes to step function, as you can see here, if I apply a step input to a dynamic system whose behavior needs to be understood, so you can get a response of this kind, and that will give you an idea about how the system is performing, and this will be helpful in understanding two things. One is the steady state response as well as a transient response, and this will also helpful in fine tuning the parameters of that particular system. So in this session, this is it. We just looked at two important elementary signals and some uses of these particular functions. In the next session, we'll look at Fourier transform representation of signals. Thank you.